Hello everyone, welcome to lecture 33 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on far field focusing for microwave antennas. So here is the lecture outline. We will first discuss about the Fabry-Perot approach for patch antenna with superstrate, and then we will conduct performance analysis of metamaterial based microwave antenna with ferrite superstrate. So let us go into the first subtopic, which is the Fabry-Perot approach for patch antennas which have got a superstrate, right. So the idea of using superstrate is to basically improve the performance of patch antenna, and this idea is not new, but it still attracts the attention of the researchers working on designing compact antenna systems and near field phase control. The near field phase transforming structures are developed for directive radio frequency or RF front end antennas for applications such as point to point communication and satellite communication. So a hard material superstrate can also play the role of giving protection to the antenna from environmental hazards, right. So there is a gap in the research. A lot of prior studies mostly focused on non-magnetic superstrates. So here in this study we will consider ferrite superstrates. So the superstrate positioning is going to be defined in terms of the Fabry-Perot cavity theory, and that is why we consider this as the Fabry-Perot approach for patch antennas with superstrates, right. So let us consider the miniaturized patch antenna on composite substrate. The design we have already seen earlier, this part. So this is basically a 1D array of metallic wires, okay, and this is the patch antenna. So you are basically seeing the side view of it, okay. So what you do here, we assume that a superstrate with identical geometry of the substrate is basically placed on top of the antenna. So it basically covers the antenna, right. And it is also assumed that the superstrate is basically situated at a distance t, okay, from the antenna patch, and it has got a material parameter of relative permittivity given as epsilon f and relative permeability of mu f, and the overall thickness of this superstrate, as you can see, is same as the thickness of the substrate, that is 2h, okay. And this is how you can consider the xy, and the z axis is along the axis of the wires, okay. So now the modeling approach, right. So in order to model this, we are going to consider the antenna patch surface as the lower surface of the Fabry-Perot cavity. So there is a cavity formed between the superstrate and the antenna. So you can see the patch antenna surface will act as the lower surface of the cavity, and the superstrate's lower surface, this one, will basically act as the upper surface of the cavity. And you can model the upper half of the cavity to have some finite thickness, and the lower half space can be modeled to have a effective refractive index of n effective, which is basically given as square root of epsilon effective, and that you have seen earlier, okay. So this is epsilon effective, okay, will be given by this formula, where you have all this parameter of the patch going in. So you can just look back 1 or 2 lectures before, and you see that this can be used, right, for designing of the patch antenna. We have already used this, right. Now let us assume that you have r, that is basically given as modulus of r e to the power I delta r, that is the full reflection coefficient of the superstrate. Capital T, which is also given as modulus of t e to the power I delta t, that basically tells you the full transmission coefficient of the superstrate. And then you have these reflection coefficients like rho L, that is nothing but modulus of rho L e to the power I delta L. So this is basically the Fresnel reflection coefficient of the cavity's lower surface, that is this one, right. And all these different phase terms that you have seen. So delta capital R is basically the phase shift due to reflection at the superstrate, delta t is the phase shift upon transmission, okay, and delta L is basically the phase shift due to reflection from the lower surface of the cavity. So, the component of the electric intensity vector E in the first zone, that will consist of the vector sum of the partial rays of the electric field component as a result of the reflections from the cavity surfaces, as you can see in the figure, right. So, from there is some partial transmission, some reflection which is getting reflected from here, again hitting the surface, some part is getting transmitted, some is getting trapped in the cavity doing multiple reflections and finally coming out, right. So, this is your substrate, this is the superstrate, the thickness of the cavity is T, the thickness of each of the substrate and this is the substrate and the superstrate both have a 2H thickness. So, the theoretical explanation of the modeling tells that from this you can obtain a formal expression of the electric intensity vector component, which is given as E theta, okay, theta is this particular angle. So, it can be written as E naught d theta times T, okay, and summation over n equals 0 to infinity, and then you have these terms, okay. So, this tells you about the multiple reflection that is going on, modulus of R dot modulus of rho L times you have e to the power minus I phi, okay, and whole to the power n, right. So, this phi is basically giving you 2 into 2 pi by lambda r into t cos theta minus delta r minus delta L. So, this is the phase factor, okay, for the cavity, okay, and then you have d theta, that is basically the electric field pattern, and lambda r is nothing but the resonant wavelength of the patch antenna. Now, this summation that you see is basically giving you a infinite geometric progression, right. So, you can actually simplify this using this formula, which is E theta. So, you can, after simplification, you can write it as E naught d theta into t, and this whole part can be written as 1 over 1 minus a. So, this is this one 1 minus modulus r modulus rho L e to the power minus I phi, okay. So, the full reflection and the transmission coefficients can then be written as r equals rho L, okay. So, these are basically the reflection and transmission, okay, or transmittance. So, this is rho L, okay, that depends on TL, TU, rho U. So, these are basically the coefficients of transmission at the lower and the upper boundary of the cavity. Rho basically are the reflection coefficients, okay. So, this way you can, these are all Fresnel coefficients basically, there are 4 Fresnel coefficients as you can see. So, with that you can find out what is the reflectance and transmittance, right. So, as I mentioned, so rho U will basically tell you the Fresnel reflection coefficient at the upper surface, TL is the transmission coefficient, okay, at the lower surface. So, TL is the transmission coefficient at the lower surface and TU is the transmission coefficient at the upper surface, and this is how these coefficients are defined. So, they are basically defined based on the refractive index, or you can say the permittivity and the angle, right. So, angles that are involved. So, this tells you about the 4 Fresnel coefficients, you can plug in there and get the reflection and the transmission. Now, taking into account that equation 2 which we have just seen here in the previous slide, this equation of the electric intensity vector component, okay, you can write the power pattern, that is P E theta, okay, that can be written in this particular form, where you have modulus t square divided by 1 minus 2 modulus r modulus rho L times cos phi plus modulus r square rho L square, and then you have d theta whole square. So, as you can see from this particular equation, the power pattern will achieve its maximum value in the forward reflection direction, that is for theta equals 0 degree, when this cos term is basically 1, right. So, this basically gives an conclusion that for you can, from this you can also obtain what is the optimal value of this thickness of the cavity for the patch parameter, patch antenna parameters and the superstrate. So, you can obtain this as T equals lambda r by 4 pi times delta r plus delta L. Okay. So, this should be the ideal thickness of your cavity, and this will provide the maximum value of the power pattern P theta. Now, with that we will move on to analyze the performance of the metamaterial based microwave antenna, which has got a ferrite superstrate. So, from the power pattern you can obtain the radiation density of the antenna with substrate. It can be written as U theta comma phi. So, this is the power pattern. Okay. So, it depends on k naught square divided by 8 pi square z naught, and then you have 1 plus cos theta whole square by 4 times this parameter, right. Okay. And then you also have this radiation pattern, which is modulus of f theta phi whole square. So, what are these angles theta and phi? These are basically the angles of the spherical coordinate system. Okay. And you will see that f theta phi tells you about the radiation pattern without the superstrate. So, this I have reproduced here from one of our previous lectures, okay, that tells you about the function f theta phi. Now, in the presence of the superstrate, the radiation pattern of the antenna will get modified like this. Okay. You will have f superstrate theta phi will be given as 4s. S is nothing but W cross L, that is the area of the patch antenna. Okay. And then you have A t divided by 1 minus r modulus of rho L. A is basically the normalized coupling coefficient between the incident electric field and the complex conjugate of the kind distribution we have seen earlier, and T is basically the transmittance that you have seen. Okay. And then you have sinc L by lambda r cos phi minus 1 times sin theta. Then you have another sinc function L by lambda r sin theta sin phi times sinc W by lambda r sin theta cos phi. So, with this you can obtain the expression for the efficiency of the antenna, which is under consideration. You can write it as eta equals modulus of T real of A minus 1 minus modulus divided by 1 minus modulus of rho r rho L times 1 by this factor, which is 1 plus j naught s divided by real of A square root of omega mu naught divided by 2 sigma I. So, all these parameters we have discussed earlier. So, you can just look back into the previous lecture and understand those. So, from that you can obtain the expression of the directive gain, which is given as d theta phi, okay, as 2 k naught s times modulus of A whole square divided by pi z naught times 1 plus cos theta whole square divided by real of A. Okay. Then you have another fraction, which is modulus T square divided by 1 minus 2 r modulus of rho L plus modulus r square modulus rho L square, and then you have this sinc terms which are basically getting squared up. So, as you can see from this particular expression that the maximum of the directive gain can be achieved for theta equals 0 degree, and the maxima of the gain can be given as G max, which will be eta d max, and the values turned out to be this, which is 8 k naught square by pi z naught. Then you have modulus of T whole cube real of A computed at theta equals 0 divided by 1 minus rho r, or you can say 1 minus modulus of r modulus of rho L whole cube times S square. Then you have modulus of A square divided by again the real part of A calculated at theta equals 0 degree plus j naught s square root of omega mu naught divided by 2 sigma I. So, when you take into account the equation 6 and 7 that you have seen, you can derive the expression for the normalized gain, which is given by G theta phi, and that basically takes this particular form. So, it is basically computed as 1 plus cos theta whole square divided by 4, and that ratio of radiation pattern f superstrate theta phi whole square divided by, that is modulus square divided by the maximum value of that. So, that is basically given this particular equation if you expand it. So, this is the expression for the normalized gain. Okay. Now, once we have obtained that, you can always plot the gain in the two planes, H plane and E plane. Okay. So, for H plane you can set phi equals 0. So, you get the expression for g h theta. Okay, that is nothing but you are putting a limit of phi equals 0 degree to this generalized expression, and this is what you obtain. Okay. For the E plane, you have to put phi equals 90 degree. So, that means you can write g e theta, that will be same as limit of phi tending to 90 degree on this generalized expression, and then you have this term. So, you can compare the two patterns and you can see that this first term is identical. You have a sinc square w by lambda r sin theta term here, whereas here you have sinc square L by lambda r sin theta term, right. So, that is the only difference, remaining other term is basically same. So, with that we can now analyze the performance of this metamaterial antenna with Faraday's superstrate. Okay. So, in order to do that, let us initially define the constitutive parameters of the antenna. So, let us choose the superstrate material, we can choose magnesium ferrite, okay, and then we are going to use these particular values of epsilon f and mu f. Okay. So, the value is 9.66 minus 0.174 I, mu f can be written as 1.2 minus 0.974 I, right. So, what are the properties of the substrate? We have considered dimensions identical to the antenna substrate, okay, that is the property of the superstrate, sorry. Okay, and then you can obtain the distance from the patch that you can calculate from the expression you have seen here. Okay. So, that comes out to be 0.0004 meter. Further, you can do FDTD simulation. Okay. So, that allows you to obtain the S11 spectrum of the antenna design with the ferrite superstrate. So, as can be obtained as, or you can see from the figure that this antenna designs are well impedance matched. So, there are two patterns, as you can see, these are basically this one, the dotted one is for the standard numerical model, and the dashed one is basically the miniaturized antenna model. So, you can see that the miniaturized one is showing a better impedance matching, and it is also closer to the theoretical value of 7.3 gigahertz, right. Sorry, this one. So, okay, you can see from the impedance matching that the miniaturized design, which is basically this dashed one, shows superior impedance matching. However, if you consider the standard numerical model, okay, that basically resonates at 7.312 gigahertz, which is basically very close to the theoretical value of 7.3 gigahertz. So, the previous epsilon f and mu f values were mentioned at that frequency. Okay, I forgot to mention there, but here you can see in the miniaturized design, okay, there is a bit of blue shift, okay, because the frequency is increasing here of the resonance, and it is around 7.404 gigahertz, right. So, now the results of FDTD simulation for the far field patterns for all the antenna designs with ferrite superstrates are compared with those without the superstrate. So, here is the one with superstrate, and this one shows you the same antenna's performance without the superstrate, and you can see this dashed dot line, this one, okay, it is bit light though. So, that is from the analytical model, we will compare with this one. Okay. So, as you can see that from these figures, you can see that the H plane has no significant difference, but for the, so overall they look similar, but E plane, this is the E plane. Okay. So, there is less coincidence of the far field patterns in the two cases, with and without superstrate. So, here we are also plotting the three cases A, B and C. What are those? They are basically A stands for standard inhomogeneous analytical model, B is standard inhomogeneous numerical model, and C is basically the miniaturized inhomogeneous numerical model, right. So, another important observation is that the analytical model for the case A, you can see that here you can see some side lobes in the presence of the ferrite superstrate, which was not the case in the when there was no ferrite superstrate. So, here you see there is absolutely no back lobe or back scattering. Okay. So, you can see the back lobe is getting prominent when the ferrite superstrate is there, and this is mainly because of the finite dimensions of the ferrite superstrate. So, right now we are going to show the presence of the ferrite superstrate can be energetically advantageous, and you will see that the appropriate FDTD simulations and analytical calculations have shown that the maximum power gain of the standard inhomogeneous analytical model, which is again shown as A, okay, that is giving the maximum gain power gain as 6.01 dB calculated at 0 degree. For the case of standard inhomogeneous numerical model, which is B, this dashed line here, okay, you are getting 5.92 dB at theta equals minus 2 degrees, and for the miniaturized inhomogeneous numerical model, that is this dotted one, for C you are getting the highest gain, which is 6.59 dB at 0 degree theta, right. Again, if you compare the efficiency model, you can also see that the analytical model is giving you efficiency of 49.37%, numerical model is giving around 46%, whereas the miniaturized numerical model is giving you efficiency of around 54.34%, right. So, why there is an improvement? You can see that the gain is improving, the efficiency is improving. The improvement is taking place because of two mechanisms. The first one is the Fabry-Paro resonant cavity effect that is working here, and the second important effect is that the increased energy stored in the magnetic component of the EM field that is radiated by the antenna, and this is coming because of the tendency of the magnetic component of the ferromagnetic superstrate to be aligned with the magnetic component of the EM field, which is produced by the antenna, and then to reinforce it by the virtue of its own magnetic fields. So, that is why you get higher gain as well as higher efficiency when you have the ferrite superstrate on top of your miniaturized antenna. So, what are the additional benefits? As I already mentioned, this you can use these ferrite superstrates. They can also serve as one of the antenna's housing panels. Okay. So, here is the near field patterns which are obtained from FDTD simulation for both the antenna designs. Okay. So, this is the antenna with those wire array which we have been considering, but this time considering the ferrite substrate. So, what you see that these are the near field plot. Okay. So, in each case we are considering the near field calculated at the xz plane. So, z is basically the along the axis of the wire. So, xz plane is basically y equals 0 plane. Okay. So, you can see the length of the wire here, and these are the two cases A and B. So, one is for the standard inhomogeneous numerical model, the other one is for the miniaturized inhomogeneous numerical model. Okay. And the same case for here it is along this xy plane. So, you can consider at any point say z equals 0 at the middle of the patch. Okay. So, what you see, the observations are based on two perpendicular field directions, okay, and the field, as you can see, are mainly concentrated beneath the ferrite substrate, okay, and you also notice that there are lower intensity of near field compared to initial dielectric substrate antenna. So, if you compare it with the previous case, you will see that the near field intensity has basically gone down. Okay. So, what does it mean? The practical implication is that when you have lower near field intensity, that makes your antenna safer for use in gadgets where there can be many more other components in the same package. Okay. So, that way it will be very useful. So, with that we conclude this lecture. So, we will start discussion about the model of rectangular patch antenna with 2-layer wire composite, or you can say metamaterial substrate, in the next lecture. So, if you have got any query regarding this lecture, you can drop an email to this particular email address mentioning the course name and the lecture number on the subject line. Thank you.